can see clearly now, the rain is gone. I can see all obstacles.
In this video, I want to discuss one of the highlights of this first part of the course, and that is Lagrange's theorem. This is Theorem 8, Section 3.2. And what it says is if you have a finite group G and you have a subgroup H, then the order of the subgroup divides the order of the bigger group. So the order of H divides the order of G, and the number of left cosets of H in G is that quotient. So you know that the order of G divided by the order of H has to be an integer because that quotient counts something that's definitely a whole number. So let's prove this. And the idea is we're going to name the number of distinct left cosets of H in G. One of these left cosets is the left coset of H containing 1. And that coset is H itself. Right? So the only things that are in the left coset of H containing 1 are things that are actually in H. Now the claim is that every left coset has the same size. If we believe this claim, then since the left cosets of H partition G, which is something we proved last time, then this shows that the size of G is the size of each coset times the number of cosets. But the size of each coset is equal to the size of H. So the size of G will be the size of H times the number of cosets. So we'll get order of G is K times N, and we're done. That's what we wanted to prove. So now we have to prove the claim. So how do you show that two finite sets have the same size? You can write down a bijection between them. So we're going to write down a bijection from H to the left coset of H containing G, some element G. And that bijection is just going to be the first map you would think of, which is take some element, little h, and send it to the element G times little h. So if we can show this as a bijection, we're done, because if you have two finite sets with a bijection between them, they have the same size. So how do we show it's a bijection? Well, surjection is clear. If you think about what the definition of the coset G times H looks like, it's everything you can write as little g times something in H. And then to see that this is an injection, let's just say, okay, if two things in the image of this map are the same, if G times H1 equals G times H2, well, let's just multiply both of these things on the left by G inverse, and we see that H1 equals H2. And that's what it means for this function to be injective. In the book, they prove this thing that's called the cancellation law for groups. And it's just this idea that if G times H1 equals G times H2, then H1 equals H2. Okay, so what have we done? We've shown that the order of H divides the order of G by showing that that quotient means something. It is the number of left cosets of H in G. So I'm going to pause and erase and talk a little bit more about this. Let's talk a little more about Lagrange's theorem. So here's a definition that we saw in the first video, but is coming back now because it's more relevant to what we're doing. If H is a subgroup of G, the index of H in G is the number of left cosets of H in G. And it's denoted with this bracket G colon H notation. So Lagrange's theorem says if G is a finite group and H is a subgroup, then the index is equal to the size of G divided by the size of H. Okay, so in a finite group of order n, the index of any subgroup is n divided by something. So clearly it's at most n. So in a finite group, every subgroup has finite index. In an infinite group, subgroups can go either way. They can have infinite index or they could have finite index. So just to give a simple example, if you take the trivial subgroup inside Z, it has infinite index. Right? Like, what are the cosets of the trivial subgroup? Every coset has one element. So the index is just the number of elements of your group G. But every proper or every non-trivial subgroup is of the form nz. And nz inside of z has index equal to the size of the quotient group z mod nz, which is n. So this is a good thing to emphasize. In the case that H is a normal subgroup, then we can put a group structure on the set of left cosets. So what is the index? It's the size of that quotient group. So when you have a normal subgroup, the index is the size of the corresponding quotient group. But index is something that makes sense even when your subgroup is not normal. All right, so I want to pause and erase and give one other kind of example. I wanted to mention an exercise that I like from section 3.1, which says, okay, let's start with two groups A and B. A cross B, where we take the underlying set as the Cartesian product, and the group operation is component-wise, meaning that how do you do like A comma B times C comma D? Well, it's A times C, the group operation in A, comma B times D, the group operation in B, is B. That is a group called the direct product of the two groups, A and B. So this is a group. And if you take the subset that's everything of the form A, something in A, comma 1, the identity of B, that gives you a normal subgroup of A cross B that's isomorphic to A. And when you take the quotient of A cross B by this subgroup, you get something isomorphic to B. So what does that say? The index of this subgroup is the size of B. It's infinite if B is infinite. If B has size n, then the index here is n. So why am I bringing this up? Well, you can start to play around with lots of examples of subgroups. Are they normal? What is the index? By taking groups that you do know and doing operations where you make new groups from old groups. So one big theme in this course is how to take some groups that you know and find new groups out of them. One way is to take quotients, and another way is to take direct products. So this exercise is all about kind of combining those two. So I recommend that you think about this one.